Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, I'm going to get started. So skip case study 2 because I won't have time for that. So I talked this morning about the kind of the mechanisms of gossip as the the epidemic is concerned, how the gossip spreads. But one thing that I was pretty vague about was this merge function. And we're going to actually look a lot more at the merge function in the next hour. So in 2008, so the case study I'm looking at is Amazon. Amazon uses gossip in a lot of different places. Originally I got involved because they took this system that I built, something called Astrolabe, and started deploying it within Amazon. And it's a DHT-like system. It uses gossip though internally in order to maintain its structure, but it's a scalable structure with these similar logarithmic type of scalability guarantees. And they started using it for monitoring configuration. It's not an improvement, but it's different. And it's hopefully it's going somewhere good. And they started using it also for routing messages, finding services within Amazon. There were a lot of machines there, even in the 2006 when I worked with them. And actually, they deployed Astrolabe on tens of thousands of machines in various continents and all into this structure. That was very exciting for me. A place where that they also applied gossip in is a system called Dynamo, which is basically a key value store. Also, more a structure like Peter described this morning. Although, it's a similar ring-based structure. Uses gossip as well, and it has these eventual consistency guarantees, meaning that when you put something in your shopping cart, eventually all replicas will see that. They also started building around the time a big storage service that now is very well known, S3. It's a storage system that for its failure detection actually uses gossip in a manner quite similar to what I showed this morning. Then in 2008, Amazon went offline for I think it was something like 6 hours initially, and there were all these headlines, like basically people feared the end of cloud computing had come. Because there were a lot of places that relied on Amazon, and suddenly it was just gone for 6 hours. This is a huge problem. And why was this? Well, they posted this thing, and was kind of amused to read that it was the gossip system. That so what does it say? On Sunday, we saw a large number of servers that were spending almost all of their time gossiping, and a disproportionate amount of servers that had failed while gossiping. With a large number of servers gossiping and failing while gossiping, Amazon S3 wasn't able to successfully process many customer requests. This was the gossip system, what I introduced to Amazon. So that was great. In my defense, I did develop some technology that they actually ended up patenting to avoid this particular situation. We'll talk a little bit about that. So what are some of the problems that come up with gossip? Gossip is a communication channel that has a limited amount of capacity. Like we're trying to get a certain amount of data through the system in a certain amount of time. And so it's not asynchronous like we talked about before. It's really a synchronous communication channel And within a certain amount of time, there's only so much information you can gossip about. And so if you try to gossip too much stuff, try to put too much information into this gossip bus, things are going to back up. So it's a problem. And so you need to tune the system. You have to set the gossip rate. You have to set the message size that you're going to use. And depending on these parameters, the capacity of the channel is affected. I'm going to talk about a few different ideas here. I'm going to, as I said before, I'm going to look at merge. What are good strategies to merge? I'm going to look at a particular strategy that I designed called Scuttlebutt. Then we're going to look at some of these performance problems that S3 was dealing with and how one might address those using a flow control mechanism. So there's a amount of information to cover, stuff to cover, so I'll go fairly quickly, but if I go too quickly, please stop me. Okay, so let's look a little more carefully at the state that a gossiper might maintain in a typical system, like at Amazon. So Amazon used gossip for monitoring their systems, for example. So you might get a table with a row for every machine. In this case, there's just 3 of them, but it could be very many of them, and a column for each attribute. So, for example, the rate of packets through the system, number. I don't know. This is information about communication, and these values inside these cells are some value like 10 here, and there's 10 ports on Jupiter, and this is a version number. It's version number 25. For here, packet rate is 0.2 packets per second, and that was version number 12. And that version number is very much has a similar function like the heartbeat that we saw before. And so what is being gossiped are these values, and only the highest version is the one that processes want to know about. So here, for example, are two of these tables, and they have slightly different information. And what you want to do is merge these tables and come up with a new table. So, for example, let's see, Venus and Mars. So this table doesn't know anything about Jupiter. This one doesn't know anything about Mars. When you merge them, you get a table which has Venus, Mars, and Jupiter in it. And then you'll see some things that get updated. What's a good one? So Venus, for example, here is version 13 is 2400, version 12 is 2300. So in the merged version, you end up with version 13. So again, these tables might be very large, but typically, if gossip is working, there will be similar to one another. The number of values in the various tables, there will be only some small differences. And so what the merge protocol, when two processes are gossiping, tries to do is to be efficient, and that means not sending the entire table from between processes, but trying to figure out what the differences are. Okay, so a bunch of different techniques have been developed. These are called state reconciliation techniques. They're actually applicable not just in gossip, but for example, if you have, say, 2 databases that are replicas, and has been maybe it was a temporary partition, and you want to now merge these databases. How do you figure out what the differences between these databases are? So we're first going to look at protocols that do so precisely that, given. So actually, we're going to look at a slightly different data structure, a set. It's a little simpler. So we're going to take 2 sets, and we're going to merge together. We'll take the union off. And we're going to do precise. So at the end, we'll have an exact union of the 2 sets. And so people have worked on that. They're not terribly efficient. I'll say a little bit more about them. So for example, we have here host A and B. They each have a set. So host A has a set of objects, A1, A2, B is a set of objects, B1, B2, most of which are the same. So how do you figure out what the differences are? Because those are the things you want to exchange. And sending the entire set is too inefficient. So one way of doing it is with this thing called the characteristic polynomial. So for host A would maintain a polynomial fa of x, which is the product of x minus each of the elements. So it has x minus a1 times x minus a2, etc. Same for host B. And then if you take divide those two functions, you end up with a rational function in which all the common elements have been eliminated. So you end up with something that's much smaller, and the degree of the numerator is the number of elements in A that are not in B, and the degree of the denominator, the number of elements that are in B that are not in A. So you end up, if these functions, if most of the elements in both sets are the same, the rational function is a much simpler function. And what you do then is you're going to sample this rational function. If you know how many differences there are, so in this case NA plus NB, if you know that there are n elements in A that are not in B, n elements in B that are not in A, you sample it in NA plus NB plus 1 point, then you can in fact find the roots of the numerator and the denominator, and that way we can find the elements. So that's what the basic idea is. See, I didn't have some more information. Of course, in general, you don't know exactly how many points there, how many elements there are that are different, and so you typically find it with binary search. You try a number, like, well, let's say 100. If you can't solve it, it was not enough. Try 200, and actually, until you find something so you can solve this rational polynomial. And it's actually pretty efficient. I've used it. There's a thing you can download from Boston University. There's some papers on it. And if that's what you're trying to do, reconcile two sets, it's a great protocol. But of course, it doesn't deal with version numbers, and it is I don't know, it's not an easy scheme, but you can download it. Another one that's at Amazon was pretty popular was the use of Bloom filters, and people actually asked me about Bloom filters yesterday. So what is a Bloom filter? Bloom filter is a relatively efficient representation of a set, although it's probabilistic, as we'll see. So again, you've got some set S with n elements. And we're going to pick some set of k hash functions, collision-resistant hash functions, but that are different, that have a range of n bits. So then for each element in the set, we're going to, and for each hash function, we're going to set a bit in a bit vector with the m bits. So I have a picture of that, I believe. There it is. So for example, here's a set x, y, and z, and there's what is it, blue, purple, and red hash function. So you apply each hash function to each element in the set, and you set the corresponding elements. And that's fairly easy to test if some element is in the set. So for example, when you do W, you calculate those three hash functions, and in this case, one of them evaluates to 0, so it could not have been in the set. Of course, you could be unlucky. You could accidentally have a case in which you take an element which happens to hash into the bits that are 1, even though W was not in the set. And so that's why it's probabilistic. In order to minimize those false positives, the number of hash functions, k, is that right? K is the number of hash functions, right? Yes. The number of hash functions you have to choose has to be log n log 2 times the number of bits in the bit vector divided by the number of elements. So you can, if you know how many elements there are in the set, you can actually, for a particular size bit vector, minimize that probability. So for example, if you're willing to spend 4 bits per element in the set and you have 3 hash functions, then the accuracy of, or the probability of not having a collision is 85.3%, I think. Is that what it means? Yes. With 8 bits and 5 hash functions, it gets better. But still, it's linear. As you can see, it's linear in the size of the set. Okay, so what you now do in order to reconcile 2 sets is when 2 processes are gossiping, they exchange their Bloom filters. And then they check each element in the set that they have against the Bloom filter of the pair. And if they find elements that are not, according to the Bloom filter, not in the other set, they exchange those elements. They send it to the other side. Now, if you're lucky, at the end of that, the sets will be identical. But you may not be lucky because you may have some of these false positives. So what you do is at the end, if you of such a round of exchange, you actually compare the sets by calculating a hash over the entire set, and you exchange the hash value. And if they're not the same, you do it again with a different set of hash functions. You keep doing that until the sets are the same. That was actually based on a fairly old paper in the 70s. There are other approaches. Mitzenmacher has a very nice approach that combines various of these things. But as you sort of can see, that none of these are particularly easy to compute. They require a fair amount of work, and they also, the amount of data that you're exchanging is pretty, can grow arbitrarily depending on how many differences there are. So we're going to look at some options to do something about that. So if you have limited bandwidth, like you have a network, you can only send so much information. You cannot exchange all differences. Then you have to decide which differences you are going to reconcile. So, for example, you might use a rule and say, well, if I have a large set of differences, maybe the only ones that I'm going to send are the ones that are most out of date. Which seems fair, but you may exchange updates that are already obsolete because they're newer updates. Well, you can say, well, okay, let's try the other option, which is the other extreme option, which is send the most recent updates first, and then you can get a starvation problem where old, out-of-date updates never make it through the system, even though they would be for other kinds of elements. So, so the idea that we're going to look at, that we applied in Amazon, is something called that we call scuttlebutt, which actually takes advantage of these version numbers. So it's not set reconciliation per se. It actually looks at these version numbers. It's much simpler. It's a protocol that's not precise, as we'll see, and that's the unintuitive part about this whole thing. So typically when you gossip, you call a merge function, you try to come up with the best possible state as a result. This doesn't even try, and yet it is eventually consistent. It's actually, we're not going to use anything complicated here. No hashes, no polynomials. You'll be pleasantly surprised by its simplicity. Okay, so the first trick that it involves is that we're not going to pick version numbers the way you're used to. We're going to do it slightly differently. So here is, this is not one of these tables, by the way. So this would be a row in a table. So, for example, we had a number of packets per second, number of flows, and number of ports, and the value and the version number. This might be, the information from a particular node in the system. So say that this is the initial state. So we got versions seven packets. Sorry, version half a packets per second. That version number 7, 8, and 9. And notice that all the version numbers are different. Now, if the number of packets per second changes to 2.7, the version number I assign is not 8, which is what you would think, but 10, which is the maximum plus 1. The maximum of the version numbers plus 1. And so now it changes again to 0.6. I take the maximum plus 1. It's 10, becomes 11. Then the number of flows changes, goes from 123 to 126. I assign a new version number, which is the maximum version number plus 1. And so as a result of this scheme, all the attributes have a different version number. It's not possible for two different attributes to have the same version number. That's part one of it. Yes? Well, so these are attributes of one single machine. And so the machine, if they're concurrent updates, would serialize them. Yes? So if I think maybe it's the same question. If two of these attributes are updated at the same time, we're just going to serialize them in an arbitrary order. I mean, these are attributes of one machine, and so that machine can serialize them. So if you've updated, so both of these, you might assign this one 11 and that one 12, or this one 11 and that one 12. Either one would be okay. But that's one part of the scheme. Now we're going to gossip. So, for example, okay. So what we now have is Venus and Jupiter, two of these machines that are going to gossip. The first thing they're going to gossip with one another is not the attributes and the versions, but they're going to gossip with one another their maximum version number. So Venus has a maximum version number 6 for Venus, and Jupiter only knows the maximum version number 4 in this case. And so they exchange a table which has only has a row in it for every machine and only one number, the maximum version number. That's round 1. And then Venus, in this case, knows that while it has 2 updates that the Jupiter doesn't have for the row Venus, and so it sends those attributes over. Mars, actually Jupiter has a more current version than Venus for the row Mars, and so it sends 2 updates in the other direction. And the last one is Jupiter has 1 update of its own row that Venus doesn't have, and so it sends 1 update in the other direction. All right, so actually let's go for a second back to, it's further back than I, so this would be something like here, this is not the same example, but you take the maximum version number 25 and here 25, they would exchange it, and because the maximum version numbers are the same, they actually wouldn't exchange anything. Okay, let's see. Okay, so now that still doesn't limit the number of updates that are going to be exchanged. So if there's a large number of updates, they're going to pick a rule by taking a subset of the number of updates that need to be exchanged. And the rule, is that already on here? No. So we'll see in a second what that rule is. Here's a little notation that I'll need. So the mu p of q of k is a pair of a value and a version number. So it's the mapping at p of q's q's another node and k is the attribute. So p is a machine, q is a machine, and k is a key for a particular attribute. So for example, in this case, the rate that P has for the rate attribute that P knows about for the machine Q is 0.5 and the version number is 4. Okay, so here's an example of what that might look like. So here is time 1. We got 3 machines, P, Q, and R. And there are 3 attributes, A, B, and C. And so what we see here is I left out all the values because it's really all about the version numbers. So, for example, P knows something about R and the attribute A, and it's something that has version number 1. And so in particular, this is only shows the information the nodes have about machine R, by the way. So this is in fact the actual value. This is what R knows about R, which is R knows everything about R. So the actual version number is 21 for attribute A, 22 for attribute B, and 23 for attribute C. But Q and P each have a older version of R's attributes. Haven't received those gossips yet. Okay, so now P and Q are going to gossip with one another, and we get to time 2. Now they're only going to gossip for the example's sake 1 delta. They're only even though clearly there are more differences. They have to would have to exchange A, B, and C. There's 3 differences that they have. We're going to limit it to 1. And the one that the rule that they're going to use is that they're going to exchange. Oh, sorry, I made a mistake. It's P gossips with R and Q gossips with R. They're only going to exchange the oldest attributes. So when P and R gossip, they find the maximum version number here is 3. The maximum version number is 23. So there's a lot of potential updates, but he only sends the R since only its oldest attribute. So in this case, A, 21, to P. Now Q does the same, gossips with R, and again R says, okay, here, let me send you my attribute for A, which is 21. And so at this time, this is the state where P and Q have the right version of attribute A, but they still have their old versions of attributes B and C for R. Right? The version numbers are 22 and 23, and whereas A has a really old version and Q has a somewhat newer but still an obsolete version. Now what would happen if P and Q start gossiping with one another? They would exchange their maximum, which is 21, and they would compare it. And as a result, they say, well, the maximum version numbers are the same, and they're not going to exchange anything. They decide not to exchange anything. And so this is why this is imprecise reconciliation. In normal types of gossip protocols, if P and Q were to gossip in this situation, Q would send to P attribute B because there's a difference, and P and Q has a newer version. However, in Scuttlebutt, that won't happen. And in fact, the key insight here is they already know that it must be obsolete. That 12 cannot possibly be the latest version for attribute Q. And we'll see why that is. So the rule is when you exchange the subset of the deltas, you only you start with the older ones before the newer ones. In this case, with the 1 delta, we only send the oldest one, and you get this invariant. It looks a little complicated. It's more it's simpler than it looks like. So what it means is that either for every attribute, it's the case that P and Q, either Q has the right version number and the right value for that key. Or if it's not the right number, the version number of that particular key is larger than the maximum that Q knows about. Let's have a look at the previous example to make that a little clearer. So it's either the case for a particular key that, in this case in A, that they have the same version number and it's the right value, or if it's not the same version number, it must be old. It must be less than the maximum that is held. And that's an invariant that the protocol maintains by always exchanging the oldest one and not the newer one. That invariant is maintained. And in particular, it implies that if the maximums of the two tables at some point are the same, if like P and R have the same version number, in this case P and Q have the same version number, the entire mapping must be the same. Right? If this invariant actually holds, and the maximums are the same, then this cannot be the case. Then it must be the case that every entry in that map must be the same. So, and that's usually the critical point in such a gossip protocol or any kind of protocol really, to identify one of these critical invariants and making sure that every operation that you do, and in this case it's that one, maintains an invariant that then eventually converges to something desirable. So in this case, when there's nothing left to gossip, they are in fact the same. So it does converge. There's eventual consistency, and I can, I'll show you a little bit about how it performs, which, as we'll see, is still leaves something to be desired. The simulation experiment has 128 processes gossiping with one another. There's 64 attributes for each gossiper, and we're going to randomly pick keys to update. The results are going to be very similar for different kinds of distributions, though. Gossip once a second, and we're going to allow 100 deltas to be exchanged in every gossip experiment. So we've got time going here on the x-axis. And this is a measure of consistency on the y-axis. In this case, it's how old the oldest attribute is in terms of time. And we're looking at 3 different protocols. 2 of them are fake. The precise ones is the ones that I talked about in the beginning. These do precise reconciliation. So at the end of a gossip exchange, the tables are intended to be the same, except that if there's a limited amount of information that you can exchange, you either pick the newest, that's the red one, or the oldest information, the green one. And the blue one is the scuttlebutt protocol. Initially, we start with 128 updates per second, and all the protocols hold up pretty well with a staleness of about 5 seconds. Then we increase the number of updates per second to 256. And now the protocols start not being able to keep up. At some point, we bring it back to 128 seconds. Protocols start being able to keep up, and then we turn off all updates, and eventually all protocols converge. And you can see that the protocol that's best is, in this case, the precise newest. Of course, you can't actually implement that protocol. You can only do it in a simulation where you have all the information. The scuttlebutt is the only real protocol there. But you see that all these protocols have a problem. They can't keep up when there are too many updates per second. I'm going to skip over the same one that looks at a different measure. The number of still attributes, you see similar types of things. So no matter how good you make your state reconciliation protocol, it may still get behind. You still need to do something else. So whether you use Bloom filters or scuttlebutt or whatever, doesn't matter. You need to be smarter than that, and that's actually the thing that I worked on at Amazon when I was there, but they hadn't implemented yet when they deployed S3. Okay, so we also need to look at flow control. Yes.
So this, either of these techniques doesn't talk about the actual merge. You still have, in case of concurrent updates, you still have a node has knowledge of its value
Yeah.
from some version and potentially a different version from someone else.
Yeah.
But it doesn't say what you should do to merge. And that's
Oh well, you know, I don't know. It does though. I mean, so in this particular case, I mean the merge. So what the processes do, they first exchange their maximum version number. So in this case, when the Q and R gossip with one another, they exchange the numbers 13 and 23, the maximum version numbers. And then the next thing they do is they say, okay, let's exchange some updates. Oldest ones first, and limit it to 1 in this case. So the oldest one in this case was 21, 22, 23. This is the oldest one. That's the one that gets sent from R to Q. That's the whole protocol.
So you might still have an update to the attribute A that gets version 21 at some other node.
Oh no, sorry. The processes are only allowed to update their own attributes, right? So there's three attributes A, B, and C, and three processes P, Q, and R. Each process has attributes A, B, and C. So P has an attribute A, which is distinct from Q's attribute A. So they all monitor the same things, like the packet rate, the version number of this or this, or that would be a bad example. The packet, you know, things of interest to that particular machine. Like typically, you know, stuff that would be, you know, that you would have sensors for, maybe the load on the machine, the capacity of the disk, the remaining capacity of the disk. Those are all attributes, and those you have the same attributes on each machine. But the machines only update their own attributes. If you want, well, I mean, so it is in some sense shared because they produce this entire table that you want to share. So, for example, in this particular thing that is far away, you know, this is the shared state. It's a table with the column for each attribute and a row for each machine. And what one does with such a table is, you know, make management decisions typically. You know, if you're going to run a replica somewhere, you're going to look at the table and say, well, this is the least loaded machine, or you're gonna, if there's some replica that's performing badly, you look at the table and see, well, what's the load on that machine? How many? What's the networking? You know, load on the machine. So that's the state that's shared. The individual cells are single writer. If you like only Mars is allowed to update these attributes. If Jupiter wanted to update anything up here, it would actually have to request Mars to do it. So let's see. Okay, so we still need to do flow control in order to deal with these big red up arrows. So the next thing we need to try and figure out, what is the rate at which updates can be introduced into the system. So that sounds a little funny. I mean, so for example, if you have the load on the machine, you might think of every time the load changes, that's an update. But what we're really doing is we're sampling the load on the machine, like sampling the size of the run queue. We can, you know, we have control over how often we sample these attributes. And so what we're going to do is to adjust the rate at which sampling happens. And that, in turn, is going to change the rate at which updates are going to appear in the system. So we'd like it to be use all the available bandwidth that the gossip channel allows us. So we want to be optimal. We also want it to be fair in that all machines have an equal amount of that gossip capacity. And we want it to be adaptive, that as the network may, or there's background load, and as more or less bandwidth becomes available, we want the flow control protocol to adapt to it. Much in the same way that TCP does all these things. You want it to use all the available network capacity. You want it to have every connection to have a fair share of that capacity, and you want it to adapt. So that's what we're going to do for gossip. So in order to make it fair, we're actually going to use a trick. We're going to use gossip itself for that. So each node in the system is going to maintain the maximum rate at which it's allowed to gossip. And then when two processes gossip with one another, they are going to exchange those rates. And for example, if I were to gossip with Peter, and Peter can gossip at 100 updates per second, and I can gossip 200 updates per second, I'm going to split the difference. I'm going to give 50 of my updates per second to Peter, so afterwards we can both do 150 updates per second. Here's another example of X and Y. So X can send 100 megabytes per second, Y can send 500 megabytes per second. And they split the difference. They're taking a total of 600 megabytes per second, and afterwards they end up with each being able to send 300. Now, if X only needs to send 200 updates per second because it just doesn't have more than that, then we don't have to actually split the difference. We can actually have Y take 400 megabytes per second, and X ends up with 200 megabytes per second, as long as the total remains invariant. So whenever two processes gossip, they each take a share, but it always has to, the sum needs to stay the same. And then in order to, so that takes care of the fairness. In order to adapt, we use something similar to what TCP does. That is, if we're gossiping too much stuff, you have more deltas than we can stick in a gossip message, or in a particular gossip channel, then we actually locally a process, when it cannot gossip all the information that it wants to gossip, reduces its maximum rate. So it just takes some off. And if there's too much information, if the gossip message actually has more room in it and you don't have enough updates to send, you increase that amount. And you do that in a way that's similar to TCP. That is, you're aggressive about reducing the rate when there's an overflow, but you only slowly increment it additively. So it's multiplicative decrease and additive increase. So, and if you then look at these three protocols again, things get a lot better. So in this case, we look at the number of deltas that a process can exchange. Again, time is on the x-axis, and some notion of staleness, or in this case, the rate. Sorry, that's not true. Time on the x-axis and the rate at which processes can send updates. And this is the amount of room that processes can exchange in a gossip exchange, which depends on the amount of bandwidth available. So initially, they can exchange 100 deltas, and at that point, we can have one. This is 128 machines. We can have about 100 updates. Sorry, one update per machine per second. Then, if we have that size, system adapts, and we can do about half an update per, or about one update every 2 seconds. And it's the same for the three different protocols. So in this case, the the choice of protocol actually doesn't matter so much anymore. They each behave the same. But of course, something like Scuttlebutt, which only exchanges version numbers, is a lot more efficient. The other ones also being fake. So here we look at the other measure, which is the staleness, the maximum staleness in seconds. Again, going from a situation where we have a relatively large amount of bandwidth to halving that bandwidth at time 90. And the protocols each adapt. This one actually has some trouble because of the way it does things. It has to a lot of backlog because it suffers from starvation because you exchange the newest updates. All the older updates have to wait, and so the staleness increases quite a bit. But it too recovers in about 10 seconds, and things get back to normal with a maximum staleness of about 5 seconds. It takes about they're gossiping once a second, so it takes about 5 seconds for gossip to disseminate. Okay, so the important things that I was trying to get across here, even though the mechanisms may not be completely clear right away, is that normal gossip that's completely blind to how much stuff is being exchanged does not give you good predictable performance. And we've seen what happened at Amazon, where machines can get completely killed by the load that gossip imposes on the network and on the machines. There's too much stuff to send around. Updates start backing up. So Scuttlebutt tries to do two different things. It tries to it adds a very simple reconciliation mechanism based on these maximum version numbers, and that's actually made its way into the Cassandra system, which is a fairly popular key value store that's used in many places, and a flow control protocol, so that these protocols adapt to their surroundings, depending on the amount of bandwidth that's available. I think that's, let's see, how much time do we have left here? So are there any questions about that part? I mean, if you want to understand the details of the reconciliation or the flow control, it's probably best to catch me offline sometime. Or there is a paper on the subject, but the important points are the ones that are here to take home points. Gossip by itself, you have to be careful with. You need to add flow control, and you need to be careful about how you do reconciliation. Yes? So the question is, if you have a database and there are, like each node has a database and there are updates that come into the system, can we control the updates? And the answer is yes. I mean, we don't necessarily need to capture every update to a cell in the database, to a record in the database. We could do, for example, every other update or every third update. Now, that's not the way you would do it, but you would, for example, only look once every second to see what has changed, or once every 10 seconds to see what has changed, or once every minute to see what has changed. And that way you can reduce the rate, particularly if you have sort of more Zipfian types of distributions where attributes, the same attributes get updated, popular attributes get updated more often than unpopular ones. Well, a lot of those updates then quickly become obsolete. So that way you can control the update rate. Yeah, that's so. I mean, like because of the synchronous nature of a gossip channel, the finite capacity in, it's not just gossip, but really any kind of channel on over a physical network. There's only so many updates you can push through a network, and so you have to do something. You cannot necessarily, if there's too many updates, you have to make some trade-off, and setting the sampling rate is the way to do it. And so what this work does is automatically finding a sampling rate that's optimal. That is, it tries to send as many updates as are possible. That's fair. Everybody gets a fair share of it. And so let's see, optimal, fair, and it adapts to what's available. So if it changes, it will go faster or slower, depending on that. Any other questions? I don't think I'm going to look at the remaining slides, actually, because I think you guys got way more information than you than you need. Yes, Peter?
I'm curious, Cassandra is presumably a multiple writer scenario, right? When do we extend it
So Cassandra is it's a dynamo-like key value store. Actually, the stuff that's used in Cassandra is, it's the monitoring subsystem of Cassandra that keeps track of. So it does membership, which nodes are there. It in fact does failure detection in this way. And for each node, it keeps track of how much capacity there is on the machines, and does things like replica placement, dealing with reconfiguration when there's been a failure. So it doesn't store the key value pairs, or it doesn't reconcile that way. For that, it uses Dynamo. But the management of the system uses something like this. And that's actually often how gossip is used. It's not so much for used to reconcile databases, for example, but it's mostly used, and I think in pastry 2, to do in the background, do the management part of things. It's very much a monitoring and control thing it's used because it's so simple and it's so robust. You can have built this very complicated protocol like pastry, which is very sophisticated with these Blackstone trees and all that kind of stuff. But then if something goes wrong, you need something to clean things up, and for that, some gossip in the background does wonders, because it can use it's a much simpler mechanism. Yes.
Also curious that going back to the same question, like the system is also processing updates from, like a database system is processing updates from clients.
Yeah.
And that generates its own traffic.
Yeah.
And then there is this gossip going on for management.
Right.
How do you decide at what point in time which of this traffic has to have more priority?
Yeah, that's a good question. I'm actually not entirely sure how that works in Cassandra. I mean, in the case of Amazon, it was actually like something a system administrator would set. It says gossip is allowed to use 1% of the network or something like that. And then if you wanted to change that to 2%, that was actually just gossiped around. The machines gossiped what that rate was. And so, again, yet another use of gossip where that rate was adjusted automatically, but based on a manual setting, somebody who set that rate. It wasn't automatically set. You could, of course, imagine that you change that administrator by some automatic rule that looks at what the load on the network is, and based on that decides how much gossip is allowed to travel on the network. But in the absence of that, like in S3, gossip can take over your network altogether, very easily, in fact. That's the danger. Yes? So I don't know. It's saying better. I mean, oops, going the wrong way. Let's see. I'm not good with this thing. Which way is forward? There. Oh no, this is not a good way of doing it. Here we go. have a bug lung around on my screen, which looks like my mouse. It's very confusing. So in this case here, I guess Scuttle does do relatively well in this particular benchmark, Scuttlebutt. But I mean, you have to first of all keep in mind that the other two are baselines. They're fake. You know, like there's no protocol that actually can find what the newest and the oldest updates are in these kinds of protocols without just you can do it when you're running in a simulation because you can look at the global state and so you can pick them that way. So these are just baselines, and compared to the baselines, Scuttlebutt in this case happens to perform pretty well. I don't know, you know, like all these protocols actually seem to perform similarly. In general, the difference is in how much computation they perform and how much overhead there is in the network. So I don't know. I don't have a good answer to your question. It seems to in the end not really matter which reconciliation protocol you use, as long you might as well pick an efficient one that doesn't do a whole lot of work, like Scuttlebutt, which only doesn't do any hashing or characteristic polynomials. The more important thing is doing flow control. Any others? In that case, I think it's actually about time for Rebecca to set up here. Thank you very much. I think that was my last lecture, so thank you for your attention.